Okay. So in the previous lecture, we studied we studied a problem in which we want to transfer the data from the I/O device to the memory using internet-driven I/O techniques. However, the main disadvantage of the internet-driven I/O technique is that it requires the involvement of the microprocessor for the transfer of data from the I/O device to memory or from memory to the I/O device. In this mechanism, the control will transfer to the internet subroutine, and now it also involves some overhead, because when you are executing some program using the microprocessor and some instruction J is executing, and let's say the internet arrives here. When the internet arrives here, the I/O device will tell the microprocessor that now the data is available with me. Okay, and now we want to transfer 100 elements from the I/O device to the memory. This program will be interrupted. What will be happen? We can have then program context switch, and after the program context switch, the control will be transferred to the ISR. The ISR will be executed. But if you look at this ISR and if you look at this problem description, so there will be some code in the ISR. So actually, if you look at this code, the data will be transferred from the I/O device to the microprocessor, and then from the microprocessor to the I/O device. In this case, we have two disadvantages. One is the latency or the overhead from the program context switch. This is one disadvantage. And the second disadvantage is that first we need to move the data from the I/O device to the microprocessor, and then from the microprocessor to the I/O device. So this requires the involvement of the microprocessor, which is inefficient. An efficient technique is to use a DMA. DMA. And in DMA is an intelligent device which can transfer a bulk of data from the I/O device to the memory or from memory to the I/O device without the involvement of the microprocessor. So in this DMA has these three registers. What we call as source. Now we have a destination, and now we have a count. So first you need to update the source. So what is the source here? Source is I/O. So let's assume this address is source. Let's assume this address is $1000, $1004, and then $1006. So what the microprocessor will do? So it will move. So what will it do? Move $1000. What is your source? I/O device. What is the base address?
1000.
This is the address of the source.
ठीक है सर.
Microprocessor will update this source, so it means it is your source. Then move $1002. What is your destination? Memory. And then move $1006. 1002. Let's do this is 2 and this is 4. $4 hash what? 100. Microprocessor has done this. It has configured instructed DMA to perform this operation. Okay? ये microprocessor, even in the previous case, it will also be done by the microprocessor. Microprocessor will initiate these values, but when the device is ready, then it will inform that I am ready. Okay? So actually, if it is I/O device, it will first collect the data. When the collected data, it will be done independently. This I/O device is connected here. It is collecting some data and collecting the data and updating these values directly. When the data becomes available, it informs the microprocessor. Okay? It's done. So when it's configured, okay, now when the device becomes available, it will interrupt the microprocessor. The DMA will interrupt the microprocessor. But now DMA microprocessor will not be involved. And DMA will directly transfer the data from the I/O device to the memory without the involvement of the microprocessor. So in this case, what is the advantage of this thing? All of these things will be done by the hardware. So these are some hardware, there will be some hardware logic here. There is some finite state machine, some hardware logic here. So in this case, now DMA will need to get the bus, the control of the bus, the control of the bus. So it will get the control of the bus from the microprocessor. So when the data becomes available, if you say to the microprocessor, okay, I want some service, I need the bus. So there are three types of signals that is required. Okay? What are these signals? These are three signals. One we call as a bus request. Bus request. Bus request is a signal that is asserted by the DMA to the microprocessor to tell them that I need the bus. So let's suppose it is 0, it does not require the bus. When it's once, what does it mean?
Required.
Now it requires the bus. It is called as bus request. Then it is a signal. So now you have now one DMA, and now it is interfaced with the microprocessor. So DMA will assert a signal which is called as a bus request. Now I want the control of the bus. Then bus grant. Bus grant is a signal that is asserted by the microprocessor to the DMA to tell it okay, now the bus is available to you. So this is now. So now what is the latency? Now it is the latency. Okay? So now there are two types of signal. Bus request is a DMA, and then okay, now if you look at here, bus request is 0. During this time, the control of the bus is with the microprocessor or with the DMA? With the microprocessor. Because the control of the bus is with microprocessor. And then there is another signal which is called as bus grant acknowledge. Okay, when this microprocessor will grant the bus, so now DMA will put its device to low, because now who is got the control of the bus now? DMA has got the control of the bus. Then there is another signal that is called as bus grant acknowledge. Bus grant acknowledge, which is a signal that is asserted by the DMA to the microprocessor. Okay? To the microprocessor to tell that now I have released the bus. So in this case, microprocessor will put its request to low. So this type of mechanism is called as handshaking. This kind of mechanism is called as handshaking. Now, I will explain this with an example. Let's assume I am the microprocessor, I am the teacher. These are the memory locations. These are the I location. If you want to transfer the data from the IO to the memory, so I will move, okay, one by one. I will move from here and move it to here. Then the second item from here to here. This requires the involvement of the microprocessor. In the second mechanism, I will delegate this power to the CR. I will ask him, okay, you may transfer all the data from here to here, and then I may go and do some other useful task. In this case, the CR, all this mechanism will be done by CR. Okay? But in this case, the DMA. Now if you look at the DMA hardware logic or the control logic, so what it's doing? So it will read from the IO device the first element E0 and directly transfer it here. Directly transfer it here. It will read from the IO device and write it into memory without the involvement of the microprocessor. Okay, now we'll try it in a more clean way.
Okay.
Now it's your microprocessor. It is your I/O device. That is your memory. That is your DMA. Now we have some address lines. These are the address lines. These are the address lines. Okay, I am not showing the address lines from the microprocessor. Okay, these are the address lines. So now it will be address lines. What is your source now? Source is your I/O. Okay, source is your I/O. So the first address that will be generated by the DMA to the I/O. That data, this address that is generated will be $2000. That data will become available on the data bus, which is element 0. That will be available on the data bus. Okay, now it's your data bus. The data bus is in green. In the second instant, the address that will be generated by the, okay. Now in this case the DMA will generate a signal which it will be I/O read, 1 bit signal, I/O read. Okay, when it's available on the bus, so it will generate an address $3000 and it will write memory read or memory write? Memory write. It will directly write to the memory without the involvement of the microprocessor. And internally, there will be some logic that it will move to the next location. What is the next location? 200, 2 or 4? It can be 2 or 4. Okay. And we need an additional information. That what is the size of each data item? What is the size of each data item? So there can be another register, additional register. Size of each data item. So if it is 1, so it means that it will increment the address by 1. If it is 2, it will increment the address by 2. And if it is 4, it will increment the address by 4. So it depends upon that whether you want to transfer 100 bytes or 100 words or 100 long words, depending on the size of it. So the advantage is this, that the transfer is made from the I/O device to the memory without the involvement of the microprocessor. And microprocessor can do some useful work. Okay, when the problem will arise, we may also encounter some delay. When the problem will arise.
माइक्रोप्रोसेसर ने डेटा बस एड्रेस बस यूज करना हो तो
when microprocessor wants to read or write some data from the
मेमोरी
now problem arises there. But if you look at today's microprocessor, if you look at in the microprocessor, okay, so in microprocessor, typically today's microprocessor has some core or microprocessor chip. We have some L1 cache, we have some L2 cache, and we have some L3 cache. If the data is available in L1, L2 and L3 cache, you don't need to access the memory. When a problem will arise?
डेटा बस की रिक्वायरमेंट जब आई या एड्रेस बस
When there will be requirement? When there is L1 hit, L2 hit or L3 hit, the problem will never arise. When there will be a problem?
मिस होगा कोई भी
Miss at which level?
एट L3 लेवल
At L3 level. When there will be a miss at L3 level, the microprocessor will need to access the data from memory. And when the microprocessor will need to access the data from the memory,
it will have to utilize the address as well as the data bus.
it cannot utilize the data bus, so in this case it will stall the microprocessor.
Yes.
But as far as the data exists in the private caches or the caches that are associated with the microprocessor and does not need the data from the memory. how we can solve this problem. Okay, transferring 100 elements is not a problem. Transferring 200 elements is not a problem. The problem arises with you would transfer huge bulk of data. Then the problem will arise. Because at some point there will be a miss in the L3 cache and it happens. How would you solve this problem?
डेडिकेटेड बस लगा सकते हैं?
If you want to have a dedicated bus, it will increase the bus size and it is not feasible from the power perspective and also from the fabrication perspective and also from the complexity perspective. How can you solve this
जो
problem?
डायरेक्ट मेमोरी एक्सेस है वहाँ पे कोई इंटरप्ट का मैकेनिज्म डाल दे कि अगर प्रोसेसर को डेटा चाहिए, मेन मेमोरी को डेटा चाहिए.
This is a mechanism that is called as bus stealing. When microprocessor will require some data, it will steal the bus from the DMA. DMA which halt its operation temporarily. Microprocessor will provide this data. It will load the data into L1 cache. Microprocessor will then continue and then it will again release the bus. So this is called as a handshaking mechanism. Now let's assume if I have dedicated the powers to the CR to transfer this data and I am doing some other useful work, but if I want to talk to the student, I will interrupt the CR. Okay, now you can stop your operation. You can stop your operation and then microprocessor will perform the operation on the memory. It will steal the bus. When it will perform the necessary operation, it will again give the bus to the CR. This method is called as bus stealing. Bus stealing, of course. Okay, all of this kind of mechanism is managed by some signals. We can call it as handshaking mechanism. Handshaking mechanism. Now, if you look at here, how now let's say there is no bus stealing. There is no bus. So actually, how does microprocessor communicate with the DMA? It communicates with the DMA through three signals. Bus request. Bus request is a signal that is sent by the DMA to the microprocessor that now I want the control of the bus. Then bus grant is the signal that is sent by the microprocessor to the DMA. Oh, now you can have the bus. So now during this time, the control is with the microprocessor, and when the bus is granted, now during this time, who is the control of the bus?
DMA.
DMA is the control of the bus. Okay, and then DMA finishes its operation. DMA finishes its operation. It will release the bus.
Yes, sir.
When it's released the bus, so the bus grant signal by the microprocessor will be lower. And if during this time microprocessor need the bus, what will it do?
ये स्टीलिंग करेगा.
When you steal the bus, so the bus grant signal will be then 0. But then it will be some handshaking mechanism with the DMA. There will be some mechanism when DMA will complete the write operation, one write operation. We can call it as atomic operation. Microprocessor will not steal the bus during the middle of a transaction. It will only steal the bus when a transaction is
completed.
It will not steal the bus during the middle of a transaction. So this is okay. So now this transaction is one memory cycle access. Now let's assume if it transferred to. So now let's assume if it's transferring the data from the IO device to the memory and it's taking 3 cycles. And if during the middle of these 3 cycles, microprocessor wants the bus, it will wait for the DMA to complete that transaction. When that transaction is completed at atomic level, when that transaction is completed, then microprocessor will. And during this time, what the DMA will do? It will transfer in the next cycle. It will increment this, and in the next cycle it will increment 3004. In the next cycle, what will it do? 200 6 and 200 300 6. And this count register will be initially 100. Then in the next iteration it will be 98. In the next iteration it will be 98. When it reaches 0, what will happen? No, it's not loop, it's hardware. It's hardware.
Release the bus.
It will release the bus. Bus grant. It will release the bus. So at this point, DMA, because now the operation is complete. Now if you look at if you remember now actually now if you look at today's powerful PCs or computers, actually if you want to transfer some data from the hard disk to the memory, like before 10 years, can you imagine how slow are these operations? Now they are pretty very fast now. Okay, so actually now if you look at the VGA or the graphic cards, okay, they are dedicated accelerators, and they are updating the VGA memory directly without the involvement of the microprocessor. If microprocessor is still involved in updating the video memory, the microprocessor can do
nothing else.
That's the reason that you need this dedicated hardware accelerator. And actually you remember when you want to transfer bulk of data like 2 GB or 3 GB or 8 GB of data, you will feel sometime that microprocessor is like slow. You remember or not? Because you want to
Transfer rate is less.
transfer rate of the hard disk is less. And sometimes the computer is hanged. Why the computer is hanged? Because now actually that kind of a priority microprocessor is now dealing with the DMA, is to initialize the DMA or to initialize the hard disk controller to give necessary information to the hard disk controller, because that information is necessary. You give all the data to the DMA. When it's configured the hard disk controller, then microprocessor. आपने कभी देखा होगा जब वो ट्रांसफर कर रहे होंगे तो इनिशियली थोड़ी देर के लिए वो आपका हैंग हो जाता है, 1-2-3 सेकंड के लिए हैंग हो जाता है, उसके बाद वो फिर वो अपडेट कर देते हैं, क्योंकि when it talks with that IO controller or the IO controller or hard disk controller, it takes a little bit time. And when it's done और उसके पास वो DMA वो फिर वो ट्रांसफर कर रहा होता है, और ड्यूरिंग डेट टाइम अगर उसको कोई नहीं, अगर वो मेमोरी चाहिए होती है किस तरह से होता है, तो वो बस ट्रेनिंग और जो मैकेनिज्म है वो उस तरह से फिर वो चल रहा है. तो आपने देखा होता है जब इनिशियली जब आप प्रोग्राम के ऊपर क्लिक करते हैं तो बहुत ज़्यादा वो टाइम लगता है, क्योंकि माइक्रोप्रोसेसर एलोकेट्स द मेमोरी फॉर दैट प्रोग्राम. वो प्रोग्राम जो है ना, इट्स नॉट लोडेड. Microprocessor gives the request to the IO device. What is the IO device in this case? Hard disk. Hard disk latency is slow. It is in the range of milliseconds. And sometime actually जब आप when you load the initial program, let's assume the program size is like 40 MB or 50 MB. So first you need to load the active pages from the hard disk to the memory, and loading dead pages from the hard disk to the memory takes a lot of time. And you will see that program will be hanged for some time when you initially click on it. But once it's loaded in memory,
तो फिर वो स्पीड अप हो जाएगा.
वो speed up. ठीक है. लेकिन आपने कभी देखा होगा जब वो ट्रांसफर आप कर रहे होंगे, जब वो डेटा आप ट्रांसफर कर रहे थे कि जब इनिशियली वो जो लोड हो रहे थे वो प्रोग्राम तो हैंग हो जाते थे, लेकिन दूसरे प्रोग्राम क्या हो रहे थे, रन हो रहे थे. It's also the job of the operating system to give different time slot to different programs. वो ऑलरेडी वो हिट हो रहे होते हैं, कैशेस भी हिट्स हो रही होती है, डेटा अगर मेमोरी में अवेलेबल है वो भी इतना स्लो तो होता है, लेकिन इतना स्लो नहीं होता. लेकिन अगर कैश हिट हो रही होती तो इट्स मच फास्ट. ओके, अगर कभी देखा होगा कि कभी आप वर्ड पे राइट कर रहे हैं वो बहुत जल्दी फास्ट कर रहे होते हैं, ठीक है. लेकिन जब आप एक बिग अमाउंट ऑफ डेटा, अगर एक्सेल का डाटा है या वर्ड का एक डाटा है, अगर 50 पेजेस का डाटा है, कब कॉपी करते हैं जब पेस्ट करते हैं तो थोड़ा सा टाइम लगता है. देखिए जब इनिशियली आपको टाइप करें तो डेटा साइज इज वेरी स्मॉल एंड टिपिकली इट हिट्स इन द कैश. व्हेन इट हिट्स इन द कैश आपको ये नजर ही नहीं आता कि हाँ, क्योंकि इट्स वेरी फास्ट. बट यू वांट टू ट्रांसफर बल्क ऑफ डेटा लाइक 40 MB or 50 MB of data, means the file size is bigger. It involves in IO operation, and IO is typically slower. And typically there are two types of buses. One is the system bus. With the system bus you have a microprocessor, and then you have memory, and then with the system bus DMA is connected, and then you have slower bus. In the slower bus there are different IO devices that are connected with the DMA and the slower bus, because IO devices are slower, so they operate at lower frequencies. Okay, so it's all the design trade-offs. So if we summarize our lectures, so we studied different type of mechanism for the transfer of data between the IO device to the memory. First technique was the program control IO. The basic disadvantage of the program control IO was that that microprocessor will continuously check the status of the IO device, and if the device is not ready, the microprocessor will be in the waiting state and it will call the microprocessor all the time. Microprocessor will be doing nothing, just checking the status of the device. When the device is ready, then it will make transfer of the data. This technique is called as program control IO. To overcome the limitation of this program control IO, now we have an interrupt driven IO. An interrupt driven IO, if the device is not ready, microprocessor can do its useful work. Okay, when the IO device needs servicing, it will interrupt the microprocessor. Microprocessor will acknowledge the interrupt, the control will be transferred to the ISR, and the program context will be saved on the stack. The ISR will perform the required operation, but if you want to transfer the data from the IO device to the memory or from the memory to the IO device, this technique is still inefficient because it requires the involvement of the microprocessor for the transfer of data, which is inefficient. And microprocessor is just involved in transferring the data and not doing any useful work. The third technique is called as DMA, and DMA is a specialized dedicated hardware in which the microprocessor instructs the DMA to perform some operation. When the DMA becomes ready, it instructs the microprocessor. The IO device is then communicating with the DMA. It is generating an interrupt to the DMA. Okay? Then, when the DMA wants to transfer some data, it will request the microprocessor to give us the control of the bus by asserting a signal that is called as bus request. Then microprocessor will assert the signal that is called as bus grant. So microprocessor will then release the bus. The control of the bus will be then with the DMA. DMA will perform all the necessary operation. During that transfer, microprocessor cannot perform a memory operation. It cannot perform a read operation or a write operation to memory. But if within the microprocessor there are some cache and there are hits in the cache, so microprocessor can continue execution. Can continue execution. Okay, in the DMA operation there is also one advantage because you don't need to store the context of the program
Under the stack.
Because you know DMA is doing it directly and the current program will not be interactive. This is another advantage.
सर एक मिनट, जब ये माइक्रोप्रोसेसर बस का एक्सेस उसे मिल जाएगा, जो बस स्टीलिंग आप कह रहे थे, तो फिर ये कहाँ से स्टार्ट करेगा? डीएमए को कैसे पता चलेगा कि मैं कहाँ तक मेरे?
Definitely, date registers.
ये अपडेट
machine insert date will be updated after each transaction. After each transactions, the source register and the destination register will be updated, and the count register will be updated. Now initially the count register was updated with a value of 100. If it has made 50 transactions,
तो ये 50
it will be 50, and the address source register and the destination register will also be updated.
इसके लिए तो हमें कोई प्रोग्राम नहीं लिखना पड़ेगा, ये तो
No, it will be done automatically. It will be done because there is some finite state machine inside the DMA. It's done in hardware. It's done in hardware. It's not in software. Definitely it's fast. And actually, if microprocessor want to perform some memory operation, so it may steal the bus from the DMA, but it will not steal the bus during the middle of any transaction.
Yes, sir.
It will steal the bus only when a transaction is
Completed.
Just like if you remember that when microprocessor will execute some instruction and an interrupt arises, so microprocessor will complete the current instruction. So in this case, microprocessor will only steal the bus when the DMA will complete one transaction. So this method is much better. It's all for today. Thank you.